as industries worldwide shift towards greener alternatives. Oxalic acid has emerged as a crucial organic compound with applications spanning pharmaceuticals, textiles, metal recovery, and biohydrometallurgy. However, traditional oxalic acid production relies heavily on energy-intensive chemical processes that involve harsh mineral acids, high-temperature conditions, and fossil-based feedstocks, all of which contribute to environmental degradation and excessive CO emissions. In response to these challenges, the focus has now shifted toward microbial biosynthesis, a revolutionary approach that not only reduces ecological impact but also integrates seamlessly into circular economy models. This video provides a comprehensive review of recent advances in the microbial production of oxalic acid from bio-derived substrates, exploring how fermentation processes can replace conventional synthesis methods. Historically, oxalic acid has been industrially produced through alkali fusion, nitric acid oxidation, and formate coupling, all of which suffer from high costs, low efficiency, and significant environmental drawbacks. Recent research highlights microbial fermentation as a viable alternative, utilizing fungi and bacteria capable of converting organic waste into oxalic acid through natural metabolic pathways. Key microbial strains, including Aspergillus niger, Penicillium oxalicum, and Sclerotium ralphsii, demonstrate high efficiency in oxalic acid production, with some species exhibiting the ability to convert industrial byproducts such as sugar beet molasses, biodiesel-derived glycerol, and cassava whey into valuable organic acids. The video explores solid-state, submerged, and surface fermentation techniques, identifying submerged fermentation as the most scalable and efficient approach due to its controlled conditions and higher yield potential. Beyond its production, oxalic acid plays a pivotal role in environmental sustainability. In metal recovery, it acts as a powerful chelating agent, facilitating the extraction of valuable elements from industrial waste, electronic components, and spent catalysts. It is also instrumental in wastewater treatment, where it aids in removing heavy metals such as lead, chromium, and arsenic, mitigating water contamination and improving public health. Furthermore, oxalic acid is increasingly being explored as a sustainable alternative to mineral acids and phosphorus solubilization from rock phosphates, offering a greener approach to agricultural fertilization. In the textile and chemical industries, oxalic acid is proving indispensable in the synthesis of high-performance materials. It is used in deep eutectic solvents for fabric modification, enhancing hydrophobicity, dye retention, and overall textile durability. Additionally, oxalic acid is a key feedstock in the production of glycolic acid, a critical ingredient in cosmetics, biolubricants, and eco-friendly polymers.
Researchers are now investigating its potential in advanced nanotechnology applications, further broadening its industrial significance. Despite these promising advancements, the widespread adoption of fermentation-based oxalic acid production faces challenges, including optimizing microbial performance, improving substrate efficiency, and developing cost-effective downstream processing methods. Future research must focus on genetic engineering to enhance microbial productivity, refining bioreactor conditions for large-scale applications, and integrating oxalic acid biosynthesis into existing biorefineries to ensure commercial viability. By shifting away from fossil-based chemical synthesis and embracing microbial fermentation, industries can significantly reduce their carbon footprint while meeting the growing demand for oxalic acid.
The future of oxalic acid production lies in biotechnology, and with continued innovation, it has the potential to become a cornerstone of the green chemical revolution. Feel free to read more about the wonderful trends in the area from the link in the description.